Hello and welcome to our presentation. My name is Matthew Griffin.
My name is Jacob Laskosky.
Today we're presenting our findings on our research that we've been conducting over the course of the past few months. This research is ongoing and currently we're continuing to collect and compile data. We want to thank Keene State College and the Center for Creative Inquiry for generously giving us a SURF grant to complete this work.
Our focus was primarily on indoor air quality in New England, observations and improvements. The faculty advisor to this project is Fernando Del Ama Gonzalo, and our project consultant for this research was Peter Yost.
The purpose of this research is to track indoor air quality, IAQ, of different residential typologies in New England, understand common issues facing IAQ in New England, create a series of recommendations to improve IAQ, and finally present a series of recommendations for future respiratory pandemic scenarios similar to COVID-19.
IAQ, or indoor air quality, is simply a measurement of the average quality of air inside buildings. We can determine this through measuring several variables, including temperature, measured in Celsius or Fahrenheit, relative humidity, measured as a percentage, carbon dioxide, measured in parts per million, or ppm, chemicals, otherwise known as TVOCs, measured in parts per billion, and finally, fine particulate matter, otherwise known as PM 2.5, measured as micrograms per cubic meter.
For this research, we tested several different homes. One of these homes is located in Southington, Connecticut, while the other two are located in Keene, New Hampshire. Here, we have included a map of New England showing the general locations of these homes. Then we have also provided a zoomed-in map of each town showing exact locations of these buildings.
The following pictures show what each of these homes looked like, with each home being named correspondingly to CSX, in which CS stands for case study. Once again, CS3 is located in Southington, Connecticut, while CS1 and CS2 are located in Keene, New Hampshire. Here we can see two graphs showing the average temperature, average humidity, and average PM 2.5 during the months of May, June, July, August, and September 2021. We can see how these averages naturally fluctuate throughout the months. In addition to this, we can even see how different national events can impact our local environment.
In this case, we can see how smoke from West Coast wildfires this summer has had an effect even here in New England, as seen in the sharp spike of PM 2.5 in late July. Understanding the outdoor conditions during our data collection times will assist us in understanding how our building and IAQ will interact with the external environment. In order to properly collect data from which we can draw conclusions, we have to ensure that the data collection methods we use are sound. During this research, we measured IAQ variables using an aware home sensor, as well as measured building air tightness using blower door tests. The aware home sensor is a small device that has a collection of sensors that allows us to measure these different IAQ variables.
A blower door is a powerful fan that mounts into the frame fitted to the jamb of an exterior door. The fan pulls air out of the house, forcing air through the envelope of the structure through penetrations and transitions. Blower doors are useful for quantifying the air tightness of buildings by measuring the cubic feet of air moved per minute, or CFM, through the envelope of the building. For our research, we used ACH 50 as a metric to determine the air tightness of buildings. ACH stands for air changes per hour. This refers to the number of times that the air indoors is entirely replaced every hour, with higher values being worse. In these pictures, we can see how a blower door is assembled and then placed into the main doorway entrance of the home. We are very grateful to have assistance from local building scientist Peter Yost in assisting in one of our blower door tests, pictured front and center. When completing these tests, the micromanometer presents us the flow of air as well as the pressure difference between inside and outside. This number is how much air is moving in and out of the building at a specified pressure, in this case at 50 pascals. This is known as the CFM 50.
Here, we can see the results as well as a chart outlining typical ACH 50 values and their corresponding attributes. CS1 had an ACH 50 value of 5.54, with CS2 having a value of 8.04, and finally CS3 had an ACH value of 5.21. The best performing home in this case was CS3, while the worst performing home was CS2.
When comparing this data to the chart we have outlining typical ACH 50 values and their meanings, we can also understand what buildings are more airtight than others. In this case, CS2 is a very leaky building. This is understandable given that the structure was built during the late 19th century, and during this time, airtightness was likely one of the last things home builders were concerned with.
Here, we can see the data collected from the case studies shown in graphical form. One conclusion that can be drawn from the temperature data is that although outdoor temperatures fluctuated greatly over the testing period, the indoor temperature maintained a rough average of 70 to 75 degrees Fahrenheit. This is due to HVAC systems and interior space heating/cooling machines.
Meanwhile, relative humidity acted inversely to the behavior that the temperature data had. Instead of remaining consistent, the relative humidity often fluctuated greatly and was often dependent on what the exterior conditions for relative humidity were. The homes that had a tighter construction fared better in this phenomenon, while homes with looser construction were the strongest candidates for this. Typically in residential settings, machines that regulate relative humidity are not installed, while machines that regulate interior temperature are installed.
Next up, we'll review the data for CO2 concentration. High levels of CO2, above 1,000 parts per million, often indicate poor ventilation and the presence of other pollutants.
Typically, the highest levels of CO2 are recorded during hours where people gathered in the house. Think morning time before work or school, and times when everyone would have returned from their days. Oftentimes, this led up to a buildup of CO2 that was too much to handle for the HVAC system to effectively remove. Meanwhile, CO2 levels were lowest when people went to school or work, and there was no one present in the house.
VOCs, otherwise known as volatile organic compounds, are organic chemicals present in homes. This value typically fluctuated with times when cleaning.
Fine particulate matter acted in the same way that relative humidity behaved. It oftentimes was dependent on what was occurring outdoors at the time. This is another sense that people do not have, and therefore it makes sense that PM 2.5 is something that is not focused on as heavily as other variables. Now we will review the results that we have found in our research. To start off, interior conditions often vary according to exterior conditions, especially seen in houses with higher leakage rates. Airtightness is key to being able to control interior conditions.
Another important consideration is existing standards created by building professional associations. One of these, ASHRAI, creates and maintains HVAC standards. Although residential ASHRAI IAQ standards may have been enough in the past, given that pandemic and COVID are continuing to be themes that appear in the IAQ discussion, we have to ask the question of, are these standards good enough? Do we need to revise these standards to reflect the expectations that continue to change as the COVID pandemic continues to evolve?
Finally, we need to consider if there should be stricter IAQ standards in general. Although temperature is the main element that is regulated in conditioned interior space, perhaps we should begin to shift our attention to other IAQ variables that have received little to no attention in the past.
As we continue collecting and compiling this data, we can begin to create a list of recommendations for existing and future structures. Some of these include increasing CFM in buildings, which in turn will remove greater amounts of virus particles in air.
Increase building airtightness and HVAC systems.
Implement HEPA filters into HVAC systems that will trap COVID-19 virus particles in filters. This could be very costly, but there do exist cheaper options that could achieve similar results. For cost effectiveness, buildings could also implement filters that are MERV 13 or better.
And increase monitoring of IAQ variables in homes and implement IAQ variable management systems. Finally, when designing HVAC systems, the architect and mechanical engineer can and should create physically separate areas with separate HVAC zones that can be used as quarantine spaces in the event of a pandemic.
At this point, we'll be opening the presentation to questions from the audience members. We want to give special thanks to our faculty advisor, Fernando Delamo Gonzalo, for assisting us in carrying out this research. In addition, we want to thank Peter Yost for assisting us with blower door testing. Next, we want to thank the individuals that allowed us to monitor the IAQ in their homes. And finally, we want to thank again Keene State College and the Center for Creative Inquiry for generously giving us a SURF grant to complete this work. Thank you.